how important would you say energy is in the laws of the universe?
I would say pretty important. Maybe one of the most important things, because I couldn't think about anything in modern physics that has nothing to do with energy. So everything basically has to do with energy. But also it's important to say that when you say the laws of universe, it's I can only talk about what I've learned and how the science fits the laws of the universe as of today, as of how I learned them. But they're also changing a lot of times. Maybe not that often nowadays as 100 years ago, but there are still a few missing parts. So maybe there is something really wrong about how we think about the universe. I even heard one physicist say that he thinks the standard model of particle physics, which is a really important model, is completely wrong as we have it today because of a single little number that is wrong. That's also maybe something that's what was happening since the last time we talked. Maybe they had something new in this way, which is really important for physics. But yes, energy is really important, and it's more interesting than I would thought, because there are only a few real different energies and also forces, but they present in different ways. So for example, you could say there's heat energy, but heat energy is basically just the particles vibrating, and we call it heat. But you could also say they're just vibrating, and therefore it's kinetic energy, which you have when something is moving at a constant speed, or also at a not constant speed, then just the energy is changing. So you have basically just energy that can take a lot of different forms, and also in the context that it's showing, it impacts how we are describing it and how we look at it. It's kind of if you're driving in a car and you make a corner and then you get pushed to the other side. But that's kind of I think it's called pseudo force, which means there isn't a force that pushes you to the side, but you're moving straight and your body just wants to move straight further, but the car is moving to the right. So if you're in the car, then it feels for you you're pushing to the left of the car, but the real thing that's happening is that the car is moving to the right.
Are we driving in Germany or America? Depends which side you're on, right? No?
Doesn't matter.
Okay.
You're also on the right side, right?
Yeah, we're on the right side. Are you on the left?
No, we're also on the right.
Oh, so it's like Britain and the rest of Europe that drives like that?
Only Britain, as I know.
Oh.
And Gibraltar also, which is a small part below Spain, but it's really it has some connections to Britain. That's why I think they're also driving on the left. But it's really small. It's smaller than New York City, I would guess. But yes, the whole of Europe is also driving on the right. I only know.
Continue with your analogy. So we're turning forward, but also it's going to the side, right?
Yeah. If you're driving and then you're making a corner to the right, then it feels like you get pushed to the left. But if you kind of look from it from above, and I can try to show it with my hands. If you look from above and you're going straight up, and then you're going to the right, like this, right? And you're in the car, so that's the car and that's you. You're just in a continuous motion, straight, and your body wants to continue this continuous motion, and then the car is going to the right. So you're just continuing your motion, but because the car is moving away from you, it feels like you get pushed to the left.
Yeah.
So that's what is called a pseudo force, because there's no force applied to you to the left. You just get pushed to the right from the car. Do you know what I mean?
Yeah, totally.
And that's so if you change the kind of view and the context of how you're looking at it, it seems different, but it's the same. And that's also true with energy. As I said, if you say there's thermal energy, so heat energy, then it's basically just particles moving and vibrating. And yeah, that's interesting about energy. And also when I'm with heat, it's really important for time in a way, because the second law of thermodynamics states that heat only travels from an area that is hotter to an area that is colder if nothing else is happening. And this kind of gives a direction to time, because most of the laws of the universe or physics are independent if you're moving them backwards or forward in time. So, for example, if you look at the moon going through the around the Earth, then it doesn't really look different if it's going the other way around. And if it would also be possible from the gravitational law. So why is it moving this way, not this way? Also with a lot of other things in physics. But with heat, it's not this way, because heat, which is a form of energy transitioning, can only move from a hotter to a colder place if nothing else is happening. Of course, you can produce heat, but then something else has to happen also. But in general, if you have nothing else, heat is also all the times is dissipating and wants to make everything equal. That's also really some physicists said if you have a theory and it goes against the second law of thermodynamics, then it's probably wrong, because it's a really, really important and fundamental thing in physics. Also, as I said, interesting implications about the era of time, and also how the universe might end if you project it forward.